Solving complex polynomial equations, really complex ones. Imagine trying to find the exact precise solutions for an equation with x raised to the power of 14. Sounds wild, right? For centuries, this has been incredibly tough. Often mathematicians thought it was impossible, mostly settling for just approximations. But today, we're diving into something potentially game changing. It's called Ezouidi's theorem. And this isn't just some minor adjustment. It seems to be a completely different way of looking at these mathematical giants. It promises exact symbolic answers, actual formulas, not just close guesses.
That's right. And our mission today is really to unpack this for you. I want to show you how Ezouidi's theorem works. We'll use a specific, pretty challenging example of 14th degree polynomial. We'll walk through it compared to the older ways, and hopefully you'll see why this is such a potentially significant step forward in mathematics. It gives you a kind of shortcut to understanding this new development.
Okay, so let's start there. Why are these high degree polynomials so, well, tricky? What's the fundamental problem? Let's look at the specific one we're using today. Px equals. Okay, it starts by 14 minus 14 by 13 plus 91 by 12. And it keeps going, term after term, down to minus 14x plus 1 equals 0. Just hearing the start gives you a feel for the complexity. That's 15 terms.
Exactly. And when you're faced with something like that, the traditional methods, the classical algebra, they often hit a wall. You usually have to fall back on numerical approximations. Techniques like, say, Newton's method. Now, those are powerful tools, don't get me wrong, very useful, but they estimate, they find approximate roots.
Right, not the exact value.
Precisely. And that comes with drawbacks. First, they can be prone to errors, especially with really high degrees or sensitive problems. You get rounding errors accumulating, little inaccuracies that can sometimes add up, and crucially, you never get that guarantee of the exact value. You might get, 1.2345, but is the real answer maybe the square root of 1.5? You wouldn't know for sure from the approximation.
And historically, there were even theorems suggesting this was just how it had to be, right?
You mentioned Abel's theorem.
Yes, the Abel-Ruffini theorem. It's fundamental. From the early 1800s, it basically states there's no general formula using only standard arithmetic and radicals, square roots, cube roots, that sort of thing, to solve polynomial equations of degree 5 or higher. So for a long time, that set a boundary. It suggested that for many of these higher degree polynomials, you couldn't get an exact solution using those familiar algebraic tools. The expectation was, well, you approximate.
Okay, so that's the backdrop, a generally accepted limit for exact solutions. But for our specific polynomial, PLX, there is a known root, XEO1. Actually, it's a root twice, multiplicity 2. That helps a bit, sure. But that's just 2 roots out of 14. Finding all 14 exactly, symbolically. That's where Ezouidi's theorem apparently comes in and challenges that old boundary. It suggests maybe we can find exact answers even if they aren't simple radicals. All right, let's get into it then. Ezouidi's theorem. What's the core idea? How does it manage to sidestep those traditional limits? Well, the core idea is it's a completely different approach. It's not about approximating, and it's not trying to force a solution into the old radical framework. Instead, it provides a systematic, almost algorithmic way to decode the polynomial. To break it down symbolically, think of it as carefully taking apart a complex machine, understanding how each gear relates to the others, until you see the underlying mechanism. It leads you to the exact values expressed as, mathematical expressions, not just decimal approximations.
A decoding process. Interesting.
And it does this using a recursive process. That's key. It's a series of steps where each calculation builds on the result of the one before it. This systematic recursion allows it to find these exact values, completely avoiding the need for numerical methods in their inherent errors. It's sort of like having a step-by-step instruction manual to unlock the polynomial's fundamental structure. Its DNA, if you will.
Okay, a recursive step-by-step decoding. You mentioned symbolic coefficients before these start things, and binomial coefficients. How do they fit in? Give us the concept.
Right. So the theorem uses a specific recursive formula. And yes, binomial coefficients, the numbers from Pascal's triangle, like an a plus bn, play a big role. The formula uses these, along with terms derived from the original polynomial, to calculate these special symbolic coefficients, the scalar values. You calculate these scalar values for each degree, from the constant up to the highest power. And these scalars aren't just numbers. They're symbolic expressions built from the original coefficients. The recursion generates them.
So each scalar is like a piece of the decoded information.
Kind of, yes. And each one is calculated through exact algebraic manipulation. No estimation creeps in. This is really the crucial part, the guarantee of exactness. Every single step, every SKR calculation is purely symbolic. You're manipulating formulas, not crunching potentially inexact numbers. This preserves the absolute mathematical precision from beginning to end. It's a level of rigor that was often out of reach before for these types of problems.
Okay, I think I'm getting the picture. It's about a rigorous symbolic transformation. So let's apply it. Back to our monster 14th degree polynomial. What happens when you run it through this Ezouidi process? What happens to those scalar coefficients?
This is where it gets really quite elegant for this specific example. When you apply the theorem's recursive formula to this particular polynomial, something remarkable occurs. A whole bunch of those symbolic scalar coefficients, they just turn out to be zero. Specifically, SR, S1R, S2R, S3R, S4R, S5R, they all vanish. Same for S7R up to 12R, all zero. It's like the process automatically filters out a huge amount of the complexity.
Wow, okay, so most of them just disappear. That must simplify things dramatically. What's left? Which scalar aren't zero?
Exactly. Only a couple remain non-zero and they hold the key. After all the symbolic calculations, you find specifically that S6R equals minus 3,000 times 14 to the power of 7, a specific symbolic value. And 6R equals plus 3,000 times 14 to the power of 14, another exact symbolic value. Just those two, out of all the potential scalar terms related to the powers of x.
2. So that massive polynomial px equals by 14, 14 by 13 plus 1 equals 0. What does it become? If most scalar is 0, the transformed equation must be much simpler.
It becomes incredibly simple. The theorem essentially shows that our original px is equivalent to a much sparser form. Px is by 14 6r by 7 plus s13r, it's 0.
Okay.
Only terms involving by 14 by 7 and the constant related to x13r, which involves s30 implicitly through the transformation, remain.
Hang on, by 14 by 7 and a constant term derived from s13r, that looks familiar. If we substitute those s6r and s13r values back in, I think. For 7, 2 plus 3,000 times 147 times by 7 plus 3,000 times 14, 14 equals 0. That looks like, wait, it's a quadratic equation, but the variable isn't x, it's by 7.
Exactly. That's the stunning transformation. The complexity collapses, revealing this hidden quadratic structure in terms of by 7. And that, of course, we know how to solve exactly.
Right, the standard quadratic formula.
Precisely. We use the quadratic formula to find the exact symbolic values for by 7. The solutions for by 7 will involve those S6R and S13R terms, maybe some square roots, but they'll be exact algebraic expressions. For instance, they turn out to involve expressions like negative 1500 smallest x word, 1500 14,001, 147 something about 147. I'm simplifying a bit, but the point is they are exact symbolic forms. Let's call them value A and value B for by 7.
Okay, so we get exact values for by 7, but we need the values for x.
Right, so the final step is to find the 7th roots of those exact values for by 7. For each value, value A and value B, there will be 7 distinct complex 7th roots. You find these using complex numbers, typically involving complex exponentials like ei2k7, where k goes from 0 to 6. This gives you all 7 roots associated with value A and all 7 roots associated with value B. That's your full set of 14 exact symbolic roots for the original polynomial.
Wow, expressed using complex exponentials, but completely precise. No approximately equal to.
Exactly. That's the hallmark of a true symbolic solution. It might look complicated with the complex exponentials, but each root is defined perfectly.
And the ultimate test, I suppose, is verification. If you take one of these complicated looking symbolic roots and plug it all the way back into that original 14th degree equation,
It should equal exactly 0. Not 0.000001, not some tiny rounding error, precisely 0. That's the power and, frankly, the beauty of an exact symbolic solution. It provides absolute certainty.
okay, that's impressive from a mathematical standpoint, but let's bring it back to the listener. Why should someone, say an engineer or a physicist, care about finding the exact roots of a 14th degree polynomial? Does it really matter in practice?
Oh, absolutely. It matters hugely. Think about fields where precision is everything. Physics simulations, complex engineering designs, cryptography, even aspects of computer science and data analysis. In these areas, relying on approximations can sometimes lead to accumulating errors. Small inaccuracies in one step can snowball through a complex calculation.
Right, that error propagation problem.
Exactly. Imagine you're designing, say, a complex control system for a robot, or modeling airflow over a new aircraft wing, or even analyzing stability in a power grid. These models often involve high-degree polynomials, implicitly or explicitly. Using exact solutions where possible eliminates that source of error. It leads to more reliable simulations, more accurate predictions, potentially safer designs, and more robust algorithms.
So it's about building more reliable foundations for science and technology.
That's a great way to put it. This isn't just about this one example polynomial. Ezouidi's theorem claims to provide a method for any polynomial degree. Having a tool that can deliver exact answers where we previously relied on estimates, that opens up new possibilities for tackling problems that were perhaps too sensitive to approximation errors before.
So, wrapping up our deep dive today, we've explored Ezouidi's theorem. We saw how it offers a fundamentally different path to solving complex polynomial equations, a symbolic recursive method. And we watched, conceptually at least, as it transformed a daunting 14th degree polynomial into something solvable, yielding exact roots, a feat that challenges long held assumptions based on classical methods and theorems like Abel-Ruffini.
It really represents a potentially significant leap in algebraic problem solving. It pushes the boundaries of what mathematicians thought was computationally achievable in terms of exact solutions. And that leads to a final thought, perhaps, for you to ponder. If we now have this enhanced ability to find exact symbolic solutions for potentially any polynomial, what complex problems, maybe in science, engineering, finance, or computing, that have always been tackled with approximations, might now be solvable definitively? Where could this need for absolute precision, now potentially met, lead to breakthroughs we haven't even conceived of yet? It really does open up some fascinating questions about the future.
So as you see here, the roots are derived recursively and solved organized surface. This formula breaks down the polynomial into manageable components known as the derived example variables instead of approximation. Let's see how this works in practice. Note that because of the recursive structure in the Ezouidi theorem, in the Mourad Sultan Ezouidi theorem, we were able to derive these roots systematically and precisely without any approximations. So you can see here, let's see the 14th degree from the equation, x is to the power 14 minus 14, x is to the power 13, plus 91, x is to the power 12 minus 364, x is to the power 11, plus 1001, x is to the power 10 minus 2002, x is to the power 9, plus 3003, x raised to the power 8 minus 452, x is to the power 7 minus 17,997, x is to the power 6 plus 7. 60,998 excess to the power 5 minus 103,999 excess to the power 4 plus 104,636 x cubed minus 62,909 x squared plus 20,986 x plus 1 equals 0. So we will write this in extended form that has to be written as x is to the power 15 minus 042 x is to the power 15 plus n1 of 42x is to the power 12 minus 42x is to the power 11 plus n3 of 42x is to the power 10 minus n4 of 42x is to the power 9 up to n11 minus n13 42 equals 0. So here the roots, the exact sum of roots of this 14 degree from equation has to be written as alpha subscript k belongs to 0 up from 0 up to 6 equal 0.2 plus xk from 0 to 6 over 14 because the highest power of this problem is 14. So I'm going to write it as 14 plus 14 into parentheses 1500 plus negative root of 2,247,000 raised to the power 1 over 7 times exponential 2k plus 1 I divided by 7 or divided by 14. You see here 14 over 14 is 1 and the next term 14 over 14 remains only 1,500 plus root of 2,247,000 or the seventh root of 2,247,000 exponential 2k plus 1 by over 7. And of course, don't forget about the negative sign because we have plus and negative. So here we summarize. So the roots has to be written as 1 plus 2 parentheses 1,500 plus negative 7th root of 2,247,000 exponential k plus 1 divided by 7. These are the 14th exact sum roots of this 14 equation, of course, using my theorem. According to me, we got, let's say, these exact sum roots. In like traditional method, which often use numerical approximations, the Ezouidi theorem provides a precise solution. This ensures that the roots we obtain here are exact and not subject to the errors that arise with numerical methods. Now that we have calculated the exact sample groups, let's verify them. Just you are going to put into the original 14 equation the exact sample groups, and we will obtain an means zero. So let's verify them. Unlike traditional numerical methods, which can introduce rounding errors, the roots here are exact. Let's substitute them back into the original equation to prove that to prove they satisfy the formula perfectly. Verification process. Here, my student and my learners, I will just show how to substitute each root into the form of x and display the confirmation that x equals 0. And I will use simple verification tools like to do this. Just go and put flag into, let's say, x equal 1 plus between parentheses root of 1,500 plus negative 7 root of 2,247,000 explanation to k plus 1 I pi over 7. Okay, so we, as you see here, we solved this point to the power 14, and whatsoever the degree of any polynomial, we apply Ezouidi theorem, and you will get your exact sample groups without your estimation or approximation method like Newton, Rabson, or Abel's method. And this method, the theorem, bypass or circumvents, let's say, the limitation of Abel's. So what does this mean for mathematics and real world applications? As you can see, the recursive method can be applied to any high degree polynomial, ensuring that we get exact solutions instead of relying on numerical approximation. This is particularly useful in fields like physics, engineering, computer science, where exact solutions are crucial for model precision and accuracy. Let's conclude. In conclusion, we have solved the 14-degree polynomial equation exactly using a Ezouidi theorem, breaking through the limitation of traditional method. We have demonstrated today, my professors and my learners and students, how high-degree polynomial equation can be solved exactly where classical method failed. With the Ezouidi theorem, we can unlock the exact sample roots for any polynomial, regardless of degree. This is a major step forward in mathematics. Thank you for listening, and see you next lecture.